Physics 2211 Lab 4, and the purpose of this lab is to use a spring mass system to observe the energy principle. And starting off with our fundamental physics principles, we have Newton's second law, which can be rearranged into the position and velocity update formulas, and all three formulas are given on screen. And now we have the gravitational constant near surface of the Earth, which is also given on screen. And then we have our spring force formula, which is negative k times the magnitude of L minus L naught times L hat. And then we have our energy principle, which states that delta E of the system is equal to the work done by the surroundings plus the heat, which is given by Q. And K, L, and L naught from the spring force formula are given on screen. And then kinetic energy is equal to 1/2 mv squared, gravitational potential energy is equal to mg times delta y, and spring potential energy is equal to 1/2 k s squared, where s is equal to the magnitude of L minus L naught. A brief preview is that we found the energy principle to be proven true because the delta total energy is always zero, meaning no addition or loss of energy in the system. Our system includes the mass, the rope, and the Earth. Our surroundings include nothing. And our initial conditions include that the mass is equal to 0.402 kilograms. Our initial position is given on screen, and we start the mass from rest. So our initial velocity is 0. The spring constant is 6.83 Newton over meter, and our relaxed length is 0.123 meters. And we find the spring constant by first starting from the period of oscillation formula, squaring both sides, and then isolating for k, as shown on screen. The total time from releasing the object from rest to the end of the video is 9.49 seconds. Here's a picture of tracking the data with Tracker. And in our computational model, we first begin by calculating what L is and subsequently finding what S is using the formulas that we've shown earlier. And then using the formulas as shown earlier, we also transferred kinetic energy, gravitational and spring potential energy into their code equivalents and added them together to get the total energy. And here's also the time step. And then in our while loop, we find a net force, which is just the force of gravity plus the force of the spring. Then we update the velocity and position of the mass. Then we also update our everything we need for the spring, which is L, L hat, and S. And then from there, we recalculate the energies once again, and we find the deltas for all of the energies, which is shown on the top right. Here is our change in energy versus time graph. Then we have our x position versus time graph. Then we have our y position versus time graph. And from the energy versus time graph, we see that the spring and gravitational potential energies oscillate and are opposite of each other, and the kinetic energy oscillates as well, being 0 when the potential energy is at its highest point, and having energy whenever potential energy is not maxed out. And then the x and y position data are somewhat consistent with the computer model, with x position data somewhat lagging behind more than the y in relation to the computer model. Possible sources of error include human error in tracking the mass in Tracker, air resistance and or drag in the experiment, or other types of energy that we did not account for, like thermal energy. So, what does it mean? Is the energy principle satisfied? Yes, the energy principle is satisfied because the change in total energy is always 0 throughout, which means that the energy in the system is just being converted into different forms, either from the potential to the kinetic or kinetic to potential, and the system does not lose or gain energy. And And then the X oscillation average that we found over a period of 5 cycles is 1.6334 seconds. The Y oscillation average of 5 cycles is found to be 1.6714 seconds. And then the difference is 0.038 seconds. And the difference could be caused by air resistance and or drag. And that could explain the lag in the real exposition versus the time graph model.